Okay, so for this first video, we're going to talk about equilibrium. So we've got a new thing that we're doing here, and basically we have a chemical reaction like we've seen before, right? This stuff kind of collides into this stuff, and it makes these things. That's what a chemical reaction is, right? They collide into each other and shift their bonds around until they create these new chemicals. What you might not have seen, though, or noticed is most of our reactions, just these two mix and make these things, right? And that's it. That's the end of the chemical reaction. This time we have arrows going both directions. So what does that mean? Well, all it means is that these guys can bump into each other, create these things, but these guys can also bump into each other and go back into these things, right? So you have two chemical reactions going back and forth. They're just the opposites of each other. And so there's a lot of chemical reactions that are like this. They don't just go one direction, they go both directions. And so equilibrium, our new word for today, is when do these things balance out? And when we say balance, we have to be very careful. What we mean by balance is that the speed or rate that these are combining into each other to make these is the same as the speed or rate that these are combining into each other to make these. That does not mean that there's 50-50 of the chemicals. It doesn't mean half the chemicals are these guys and half the chemicals are these guys. It just means that these guys are turning into these and these guys are turning into these at the same speed. And so the reaction kind of settles into a dynamic equilibrium. There's still reactions happening, but for us looking at the beaker, we won't see much because it's all kind of balanced out. So let's kind of look at this inside of a beaker here, right? So just like our chemical reaction, we have a bunch of stuff in here. At the top right, you can kind of see that it's NO2 and N2O4. That's the two things we have in here. So if we press play and let these guys react together, right, they bump into each other. We see collisions, we see molecules breaking down, molecules coming together to synthesize. Let me reset this real quick. One thing I want to look at before we start here is this bar graph. Right now, I have it set up so that there's, I put an equal amount of each chemical into this beaker. There's 8 and 8, right? So it's 50-50, perfectly balanced. So then the question is this at equilibrium? And a lot of you might be thinking yes, but no, not necessarily. The only way this is at equilibrium is if they stay 50-50. So let's see if that happens. So if we press play here, right, we see all these reactions happening. Things are colliding into each other, converting into other things. Notice our bar graph, though. They're not staying 50-50. Our NO2 is going up and up and up, and our N2O4 is going down. So these chemicals are not at equilibrium when they're 50-50. I've noticed that the bar graph isn't changing as much as it was at the beginning. So the change is kind of starting to slow. Notice the chemicals are still reacting just as fast, but our change in concentration here is kind of settled out. And if we like switch this to a line graph, look at what happened. So remember that orange line is the NO2. At first they were 50-50. Now the orange is way up there. It's closer to like 13 concentration, whereas our N2O4 is decreased. It's down to about 5. Notice though that the line is pretty much flattened out at this point. What that means is this is equilibrium. These chemicals are at equilibrium when there's about 13 of the NO2s and about 5 of the N2O4s. That's equilibrium. Notice that their concentrations are not changing anymore. They're just kind of flattened down into this flat line. If we look at our beaker, though, there's still a lot going on. There's still a lot of reactions going on. There's NO2s combining into N2O4s. There's N2O4s breaking down into NO2s. But they're both doing it at the same speed now, and so the reaction kind of settles, okay? So this is equilibrium. And another example of this that's really good is this video here. So if you think about this guy on this escalator, you can think of this guy as one version of the chemical reaction, right, going forward, and maybe the escalator is the other reaction going backwards. So when he starts walking on this escalator,
the escalator is going down.
He's going to start walking upwards,
down
and the escalator is going to be pushing him downwards, right? And so notice right now he's not moving. Like he is moving forward, but the escalator is moving down at the same speed he is. That would be equilibrium. Now he has started to increase his speed, and the escalator hasn't. So he starts to move upwards. He's not at equilibrium. Notice he doesn't have to be halfway up the escalator to be at equilibrium. That is the biggest misconception. Equilibrium does not mean 50% or half or anything like that. He's at equilibrium when his speed going up is the same as the escalator's going down. He could do that at the bottom of the escalator. He can do that at the middle of the escalator. He can do that at the top of the escalator. It doesn't really matter. Equilibrium is just when the speeds of change are balanced, okay?